Hi there, everyone. So we're resuming the workshop here with the last of the algorithm sessions, algorithm 3. And we've got a couple of interesting talks here. So the first of these is going to be given by Filip Wojcicki. So he's a PhD student in the Department of Computing at Imperial College London, and also completed his undergrad degree there in computer engineering. His research is in the intersection between high-performance computing, compilers, FPGAs, machine learning, and numerics. Most recently, he's investigated how microscaling data types could be implemented efficiently on a RISC-V vector cores and how they compare to ASIC-based approaches. And that experience led him to his research on numerical methods and interaction with block floating point formats like MX. And he's particularly interested in how different platforms, such as RISC-V and FPGAs, can be exploited for these operations through low-level software hardware co-design. And we're going to hear more about that now as he tells us about accelerating transformer neural networks on FPGAs for HEP experiments. Take it away.
OK. Hello, everyone. So yeah, my name is Filip, and today I'd like to present our work on accelerating transformer neural networks on FPGAs for high-energy physics. So the idea here is to tell you about the process that we went through and what we've managed to achieve, but also hopefully to make it slightly more general for you to see some common points, right? Some pitfalls that we had or some like techniques that we used to achieve what we did. So the motivation for the actual problem that we had was that particle physics really requires real-time detectors. So this means both ultra-low latency as well as very high accuracy. And in the past few years, transformer neural networks have been yielding great results in a number of domains. And the idea here was, OK, let's try to adapt it to jet tagging. So many of you who work here at CERN probably know what's jet tagging much better than I. But my understanding is that it's this method of finding what was the origin of a particle jet. So in the Large Hadron Colliders, when two protons collide with each other, they create a number of different particles that go through a process of decay, and what you actually see at the end is not as interesting as understanding what was the process before that. So in our case, the data set is like 5 jet classes simulated on some of the existing data with quarks, gluons, and bosons, I think. And following on the background, so the actual transformer and the underlying attention mechanism. So this is a neural network proposed by DeepMind a few years ago. And it uses this attention mechanism for global dependencies. And there is no recurrence, which is something that was quite popular before in recurrent neural networks. And it only uses this residual connection. So the skip connections that you see, basically, it is quite slow, yeah, on here and so on. And normally it was designed for natural language processing, right, like voice and text. However, it has been proven to be like the state of the art in many domains. Like obviously now we have LLMs, right, large language models, but also things like computer vision with vision transformer and so on. And this has also been brought a few times already today, right? This notion of high-level synthesis and HLS for ML. So just to quickly give you like my understanding, right? So if high-level synthesis is this step above, right, Vivado and HDL, then HLS for ML is like one layer above, right? It's this open source workflow. So we've used it in a way where we've set the project with it, right? So that the FPGA has all the connections and so on. However, at the time, there was no support for transformers. And it's actually still an ongoing effort, right, a few years after. So we simply like used the existing templates and we left everything blank. And those blanks were our like core work, right? So filling them with the actual HDL. So the two main challenges, hopefully somewhat applicable to everybody. The first one was that simply the transformer design that we chose scales quadratically. You can see it in this derivation. The most important part is in this box, right? There is this d squared. So it's inherently not so good. However, if you use FPGAs as accelerators, you can meet some real-time constraints that we had. These were particularly at the CMAS experiment here at CERN. There is the kind of hierarchy of triggers. The L1 trigger, which is the first one, requires microsecond latency. So the hope was that if we use FPGAs, we can meet it. And the second challenge, very applicable, hopefully, FPGAs simply take quite a long time to develop, right? Like, it's not like with software, you write a few lines of code and you just hit play, right? So the idea here, by using HLS4ML, but also other techniques that I'll mention, was to actually make this implementation as well as the whole, design space exploration much faster. So the novelties that I will cover in more details in the coming slides can be brought into 3 categories. The first one was the actual design of this network, right, from software to hardware. Then the specific optimizations that were targeting FPGA to actually benefit from the use of FPGA. And lastly, it's about the quantization, and more specifically the post-training quantization, which allows us to vastly save on the resources. So starting with the low latency architecture, so we took the existing design from DeepMind and we went through a series of high-level optimizations. And by optimizations, what it really means here is simplification steps that did not lead to accuracy drop. So first of all, there was the weights and biases matrix splitting. So instead of on GPUs where you usually have them in big blocks, right? Here, you obviously want to split them into smaller forms so that you fit the actual granularity on FPGAs, and you also have it in the specific places that you require it. Second, there was the change from the functional encoding. So this is the step that usually happens at the very start of a transformer, which requires some actual computation to happen, to a learnable parameter, right? So instead, this was a learned during training, and afterwards ended up being a simple matrix multiplication with a weight. There was also a number of exotic activation functions which do not map to hardware so nicely. So again, it was the process of identifying how they can be simplified without losing accuracy by using hardware-friendly alternatives. And quite obvious as well, the division, right? You never really want division in your project because it doesn't work well on FPGA. So it was the matter of finding where it can be changed to binary scaling and doing the appropriate arithmetic, right, to make it work. And lastly, quite interestingly, there were a number of normalization layers, right, which you usually have to keep the design from blowing up numerically. And we started with simplifying them, but we found out that in this particular case, because the design is so simplified already and the data that we use was so simple, there was actually no need for normalization layers, which was just some performance gain for us. So for the inference comparison, so not surprisingly, we beat the state of the art because it was on GPUs. So this is not so interesting. However, what is more interesting is how scalable we remained while having a design that is this new, novel, complex thing, which ended up basically being one of the best in terms of the inference, in terms of the accuracy, and having significantly lower parameter count than other designs. And as you can see in the bottom table as well, there is still a lot of performance to be gained from using more resources. So in this case, I think it was a U250 board from 5 years ago, and it was only used significantly in terms of DSPs, other not so much. And coming to the second novelty of the hardware optimization, so there was quite a lot of them. This was the bulk part of the project. And I chose the 2 most interesting ones, which I also think are the most general, applicable to everybody. So the first one was this log softmax notion. So it appears in some places in this neural network. And if you just literally take the logarithm of a softmax, it's extremely not nice for FPGAs. You can see this is the top design here. And by simply applying logarithmic properties and by knowing what you're looking for, right, knowing how FPGAs work, you just, you find a different way to represent it, which is not even an approximation, right, this is an equivalent thing, right? So you just simply gain performance here without any drawbacks. And the second thing for us was there is this Einstein summation that gets used quite a lot in machine learning, especially when it comes to mathematicians and physicists. So it's very nice, it's very high level, but it doesn't really tell you what's happening exactly in the hardware. So in this case, we made this way to transform it into high-level synthesis where you can easily see what's actually happening. It's human readable. And the point here was that obviously this allows you for optimization, but it just tells you the full story, right? You can see how the memory is getting used, how the how the I/O will be used, and so on. And by spending quite a lot of time in this lower level optimizations, we've actually fully mapped this pipeline that's happening behind the scenes to our design, right? This is not always the case if you're doing a high level synthesis. This is obviously if you're doing, let's say, Verilog. But in our case, this allowed us to fully see what's happening, how does each stage actually behave. And like what you see now seems quite simple because all the stages are like roughly the same size, but this was like the key point that led us in our optimization journey, because let's say we saw that the log softmax is taking 10 times longer than we expected, and we were like, okay, it's time to go back, it's time to actually improve it, right? So it's not the main bottleneck. And by also doing so, we've created like closed form formula, which was quite handy for us, especially in this like research environment, because this allows you to like really understand what will happen if you change some parameters. So let's say a new paper comes out and it says that hidden dimension size should be triple, right? And you know exactly that, oh, you can just do it, right? It will work. You will have the latency budget still there because you know that it will not violate anything. And then the last point is about quantization, and specifically the post-training quantization. So this idea in general is that like after you've after you've trained your network, right, you've deployed it on an FPGA, you want to make it better, right? So the obvious thing here is you try to see which variables, which data points can be expressed in better so-called like precision. So it's usually lower precision, it's usually like integer instead of floating point, and so on. So there is like a number of ways to do it, like the very naive way. If you just think about like each possible like brute force combination, it's enormous, right? So the way to go here is we created this sort of like guided walk through the design space where you put the variables, the different like data points of inside the network along like the data path, and you go one by one. You try to see which one can be made smaller, which one should be made bigger, because maybe they will actually benefit the accuracy heavily, right? You shifted the decimal point around, and by going through the whole network, we've made a 64% total bit rate reduction compared to FP32, which is quite commonly used, right? Especially then in on GPUs and CPUs, and there was only a 2% accuracy decrease. And the number itself was like sort of customizable, because at the very start of this walk, you can set the limits, the constraints that you want the walk to stay within, so you don't end up with a design that's maybe very resource friendly, but is actually very terrible, right? And in here you can see the particular diagram of our use case. So on the bars you can see the representations of the numbers of the variables precision. On the along the x-axis is like the data path, so like the data kind of moves along. And then like the up and bottom parts are like the integer and fractional parts. And what's most importantly here is not the actual numbers, right? It's that it varies quite significantly. It's quite chaotic. So obviously you can spot some patterns. There is obviously for example, similarities between weights with each other and accumulators with each other. But the overall thing is it's infeasible to reproduce manually, right? You usually wouldn't even go as low as having a different precision for every single thing in your design, just because it's not really feasible. But by doing a somewhat optimized, somewhat smart algorithm, we've managed to significantly reduce it with only an accuracy that was allowed in our case. And now let's talk more about quantization. So in this case, quantization over training. So it's not a novelty per se, but it was just something that we spent quite some time. So obviously, when you train the network on a GPU, you do it with floating point numbers, but then you suffer the penalty of the quantization error, right? When you go from this onto an FPGA where you usually want to do a fixed point precision. So the idea here is to actually train in fixed point precision, which is not very quick, but it can lead to significantly better results. You can see how it varies. It varied quite a lot. It was quite interesting because it wasn't obvious, right? It wasn't just that at every point, more bits means better, right? And there was also a number of frameworks, so 2 from PyTorch, 1 with Brevitas. I think there's even 1 more from PyTorch right now, and QPyTorch, and all of them try to achieve a similar goal. And I'm not saying which one is better or worse, but for this particular case, the QPyTorch was extremely interesting because of the novelty. So on this slide, you can see, so for example, in something like Brevitas, you would expect the layers that you are working on, so let's say in this case, the attention and the transformer, right, to exist in a quantized version. But if you're doing something that has only really been done a month ago, right, and you are coding it yourself, there is no quantized version, right? You would need to spend time to do it. And maybe you could, maybe it's in the scope of your project. It wasn't for me. So in this case, I use QPyTorch, which doesn't actually do the fixed point precision as accurately as it should. It's really emulating it. And what it does, it allows you to use the already existing layers, the PyTorch code that you have, and just like intertwine it with like quantize, dequantize steps. And this is not like the actual picture of what's on FPGA, obviously, but it gave the result that was like much better than not having it all together. And now as for the future work in a project like this, obviously the first choice would be just to look for an alternative transformer design. This can be applicable to any kind of problem, right? Maybe you just start with a different algorithm altogether. So this hopefully reduces the complexity, probably not so much that you don't need an FPGA, but maybe you have more resource budget and so on. And this is like from the compute side, but I think what's even more interesting for like the future of this kind of projects is using like quantization, so both the post-training quantization, but especially the quantization aware training. So using things that are like much more exotic than normal ints and floats, for example, microscaling data types, which is something that I've been working on recently, which is this type of block floating point numbers, which work especially well for FPGAs where you have like the full granularity, right? There is no preset notion of bits, right? You have as many bits with as much configuration as you really need. So in conclusion, I've presented you our approach of how we went from a software idea to a real product, real like hardware implementation of this accelerator. I've mentioned the number of optimization steps that we took, as well as I've talked about quantization, especially the post-training, how it gave us like performance for free, and lower resource utilization is better for everything, for compute, for memory, for I/O, right? So that's all. Thank you very much. You can scan the QR codes for the original paper as well as the project repo, and if you had any questions, feel free to email me. Thank you very much.
Thanks. Very nice talk. Does anyone have any questions? Maybe you first.
So if I understand, thank you for the presentation, very nice. If I understand, you use a QRT which is not exactly simulating what the FPGA does. So did you try to measure the accuracy after this QRT under architecture? Did you validate that the QRT is close enough on FPGA? Once you take, so the QRT gives you new coefficients, and you plug these coefficients into your architecture?
So in general, so we've had like both the simulation and we've done the synthesis, and it was like obviously smaller than, the accuracy was obviously smaller than like the original software version on GPUs in PyTorch, but it was like close enough for us. So I think the overall, I'm not sure if I reported, but it was like within 1 or 2% of basically the starting point, which was like the kind of the bottom line for us.
My question is really about the possible difference between the QRT you use, which has these quantized layers, which do not reflect exactly what happens in FPGA. If there's any difference between the QRT when you build the QRT?
I'm not sure I fully understand, but I think the answer is no. As in like, so which slide are you specifically referring to? As in?
This one.
This one?
Yes, this one. So you have these quantized layers?
Yes.
On the FPGA, the quantization is within the architecture?
Yeah, so obviously, so this is the point that...
Eventually, this is not learning exactly for your architecture, for your hardware. It's learning for an approximation. I wanted to know if once you have done this quantization in this framework, and you run it on FPGA, you get the same accuracy.
Yes, so very similar. So the point is that it's not like trivial to do the QPyTorch thing. It's not just adding a line of quantize. You actually like highly specify what's the quantization, what's the dequantization. So you like kind of force it, right, to be you try 17 bits of accumulators with 27-bit mantisas, and so you know what I mean. So it's obviously not as good as if you set the Brevitas pipeline, right, to be like, this is the target hardware, right? Use it. But it was like significantly faster, and the main point here, it was probably not optimal, but it was significantly better than just going from floating point trained network on GPUs to straight up putting it on FPGAs. Thank you.
So Sam, for the talk. Since you mentioned the transformer takes around 5,000 DSPs and around 25,000 LUTs, I'm kind of wondering if that is bigger than one superlogic region on the 13P, which is kind of the largest.
Sorry, can you speak a bit louder?
So that model you mentioned is taking around 250,000 LUTs and around 5,000 DSPs. That's more than one superlogic region. So for the latency you mentioned here, did you consider the cross superlogic region, and is that post, place, and lot?
I'm not sure. I think we've considered like basically I think this might be just of one region. I'm not exactly sure, like as in of the one PR region. This is your question, right? If this is crossing more than one PR region.
What is the chip? Because 5.5 thousand DSP doesn't exist in one superlogic region.
And then what is your question? Sorry.
And that means you are crossing one superlogic region unless you are using a super large chip. And because you are reporting a latency of 18 cycles of 5 nanoseconds.
So I think it was fitting within one region. So this was specifically on the U250 board, which was quite like top notch back then. So I think it was fitting, as in like, you know, there were no issues in terms of like timing constraints or like any violations in the synthesis.
So everything is after routing.
Sorry?
Everything is after routing.
Again, sorry?
Is the result you are reporting after routing and with timing closure?
I believe so, although I will need to check because this is quite specific and I haven't worked on this recently. But we can discuss it later because I'm not exactly sure. I can check it in my code.
OK, thank you.
Thank you.
Hello. Specifically in this slide, you mentioned that for inference, the FPGA design can be 3 to 5 orders of magnitude faster than the state-of-the-art GPUs. Could you tell us more details about which neural models have you implemented or
OK, so it's basically between like these models and there's like the current, like what you see here is on evaluation on the GPUs. And there is also like an evaluation on FPGAs, but only for some of them. It's basically I was trying to do like the kind of background for this project, but it was not very like kind of comprehensive because some people were, in this field of jet tagging, some people were only showing like FPGA solutions, some were showing GPU solutions. So this is why I give like a wide estimate of this is how much faster it was than GPUs. And there was no like direct correspondence to any FPGA design back then.
But then how you ended up with these values? How would you make this comparison? Or is something of the reference?
You mean the number 10 to the 3 to 10 to the 5?
Exactly, yeah.
So I think it's from another table in my original paper where basically like it's a bit of a stupid comparison to start with, which is why I don't make it the whole point of this slide, right? Because obviously if you do a highly customized solution on FPGA, right, you expect it to be faster than a general solution on the GPU, right? So the point here was that this was just like a bit of an unexplored space, right, like jet tagging on FPGAs, but it was already proving to be much faster than like the solutions on GPUs from what the authors of the papers reported. So I didn't like, recreate the solutions on GPUs myself. I just claimed the numbers that they had.
Okay.
Thank you.
OK. Yeah, maybe we want to thank Filip again and move on to the next talk.
Thank you.